Hello class, this is the fourth and last session we'll spend on the Rankine vapor power cycle, and we've been exploring ways to improve the performance of the power cycle. We started by looking at superheat for the turbine inlet. Then we proceeded to looking at the effect of staging multiple turbines and how that could improve the performance by allowing the exit state to have higher quality and a step towards more realism. Then we looked at the effect of reheat between intermediate turbine stages as a way of further increasing performance as seen through efficiency. And the subject of this lecture is going to be regenerative feed water heating, which should provide even greater thermal efficiency for plant performance. Okay, the slide in front of us shows the concept for open feed water heater. There's also a closed feed water heater, and we're not going to discuss that. It gets a little bit more complicated. I think we'll focus on open feed water heaters. Okay, let's start by looking at pump 2. So we provide power input through work to drive pump 2, and that increases the pressure of the working fluid from state 6 to 7. So we've got a pump as usual. We go through some sort of a boiler, steam generator device to put energy into the fluid from an external source. That's the same as before. That takes us from state 7 to 1. And then things get a little interesting with the multiple stages of turbines. Notice how the boundary is around all of the stages together. So we'll claim that as a control volume. And we have mass flow rate going into the turbine. So there's M.1. That is our total flow rate for of the coolant for the power plant, or the working fluid for the power plant. And now with regenerative feed water heating, we take some of the fluid out after the first turbine stage, but not all of it. So we have out of the first turbine stage, M.2, and then out of the out of the exit of the second turbine, state 3, we have the other mass flow rate. Okay, I'm going to move down here to the bottom open space, and I'll apply the conservation of mass on the turbine control volume. And doing that with the usual assumptions of steady state, uniform flow, I find that the total mass flow rate of the system, M.1, must therefore equal the sum of what's being bled off at the exit of the first turbine and the remainder that's leaving the exit of the second turbine. Okay, now I'm going to do some algebraic manipulation. I'm going to divide both sides by the total mass flow rate. Okay, so I end up with 1 equals ratio and at this point we're going to define, so we'll let variable y be defined as M.2 over M.1. So y represents the fraction of the fluid that we bleed off after our first turbine. And if that's the definition of y, then substituting that back in to the conservation of mass shows us that M.3 over M.1 must be equal to 1 minus y. So this is just a convenient way of reducing this to a fraction. Okay, let's go back up. So now hopefully you can see why we have 1 representing the total mass flow going into the turbine stages, Y representing m.2 over m.1, the fraction of fluid leaving the exit of the first turbine stage, and then 1 minus Y indicating state 3, the fraction of fluid that's leaving after the second turbine. Okay, so now we have 2 fluid paths. One fluid path from state 2 is going to feed into what we're calling an open feed water heater. That is essentially just an open tank, an open mixing tank. So that is a control volume where you have fluid entering from state 2, the exit of the first turbine. You also have fluid entering from state 5, and that's mixing together, creating state 6. So we could apply the conservation of mass and then the first law to analyze that open feed water heater. What's happening from the other fluid stream, represented by state 3 at the exit of the second turbine? That then feeds into our condenser, where we have heat transfer out to the environment. I guess I should go ahead and list the heat transfer in through the steam generator to be consistent. And now note that because we have that open feed water heater, we need 2 pumps. So we need a pump to pump the fluid in from the condenser to the feed water heater, and then we need a pump to pump the fluid from the feed water heater into the steam generator. What does this do to our property diagram? Well, let's look at the TS diagram here on the right. We'll start with pump 1. State 4 is a saturated liquid, and the pump is increasing the pressure of the fluid to state 5. 5 to 6 represents the open feed water heater. Let's see here. 6 to 7 represents pump 2, and 7 to 1 represents the steam generator. We have to sort of keep track of the different fluid streams at this point. I'll note that here I have my total mass flow rate, M1. Also through the turbine, at least the first stage turbine, I have total flow rate M.1. And then at state 2, so 2 to 6, I have M.2. And state 2 to 3, the second stage turbine, I have flow rate M.3. So I have different amounts of fluid flowing through the different devices at different points in the cycle. That's the take-home message. I can no longer assume I've got the same mass flow rate through everything.